Now we're ready to prove the first variation formula, which will show that length minimizing curves must be geodesics. So let's first explain the setup. So the setup is we have some curve, gamma, that is admissible, so it is piecewise regular. Okay, so let gamma be such a curve on M with unit speed. Every curve has a unit speed parametrization, so this is not a restriction. Now we let big gamma here be a proper variation along this little gamma. Remember, a variation along gamma would just be a family of curves, one of which, right, the curves at 0 would be this gamma, and a variation is supposed to be proper, is said to be proper if the endpoints of all the curves in the family are the same as that of gamma. So here that would be this is an example of a proper variation. Then recall we defined the variation field V of gamma to be the vector field along the curve little gamma here, right? Defined by this formula, so it captures how this little gamma vary in this family. We can view this family as deformation of this gamma in the direction of this vector field. Alright, so what does the first variation formula say? Intuitively, it's saying that this change in arc length is determined by two things. Number one is the component of V in the direction of this. This is the acceleration vector field of gamma. From this term, we see that deforming the curve gamma in the direction of acceleration, so V is in the same direction as the acceleration, will actually shorten its length. So if gamma was to have minimal length, then it should have no acceleration. Because if there is acceleration, there is room for shortening the length by deforming it in the direction of the acceleration. That's why if gamma has minimal length, then it must be a geodesic. It has no acceleration. But I lied there, because just to have zero acceleration doesn't mean that it's gonna be a geodesic. We also need to show that gamma is smooth. This is where the second term comes in. Right, so I never explained what these AIs are. So we said from the beginning that gamma is an admissible curve. That means it's piecewise regular. That means that we can partition the domain AB into subinterval finitely many, such that on each of these subinterval, gamma is a regular curve. That means that at every partition point, AI here, we get two tangent vectors. One corresponds to this left regular segment, and one corresponding to the right regular segment. This term delta I here corresponds to their difference, right? Thus this dot product is the component of the vector field V in this direction. So what the first variation formula says is that if we deform the curve in this direction, then its length is shortened. So in other words, look what happened. What happened when we deform the curve in this direction? We're just rounding the corner. So this expression says that when we round the corners of this curve, then its length is reduced. So that means that when the curve is of minimal length, we should not have sharp corners anymore. Because if there is sharp corner, then we can still reduce the length by rounding the corners. That means the minimal length curve must be smooth. Thus, we see that a minimal length curve must be smooth and must have zero acceleration, so it must be a geodesics. Alright, so that's the intuition. Let us now actually prove this.